Welcome to topic 1.2, mass spectra of the elements for AP chemistry. All right, let's get into it. Mass spectra of the elements is really a fancy word for saying figuring out the atomic mass unit of our elements on the periodic table. Now, mass spectra calculates atomic mass unit by the average. This number is the average of all isotopes. And you notice that some don't have a mass. Starting with 84 all the way over through this, and even some of these. Now, there's also no mass for technetium on my periodic table, but also even on the AP. Well, why is that? Well, that's because those particular elements are either highly reactive, radioactive, or man-made elements by in a lab by smashing nucleuses together with neutrons and protons and alpha beta particles, and they have such a short half-life. We're talking like sometimes less than a second, sometimes milliseconds. So there's no way to actually average or even find if they have isotopes and even take a mass. So all the other numbers, that's why there's decimals behind them, because it's an average of all the different isotopes. So when you took chemistry, you might have learned that some metals have different charges. Well, that ties into the individual isotopes for these elements. And some elements can have 4 isotopes, some can have upwards of 12 different isotopes. So how do we measure that? Well, there's a machine that is called mass spectroscopy, or mass spec. It's an analytical chemistry lab technique that separates the components of a samples by their mass and breaks them down. So here we have chromium here. It's got a bar at 50, 52, 53, and 54. So this is chromium. It has 4 naturally occurring isotopes in nature. So an average atomic mass is the average of all the isotopes, and the mass number is specific to that isotope. So here for chromium 50, we can write it like this, or we can put the elemental symbol, the mass number or the isotope number goes on top, and the number of protons, which is the atomic number, goes on the bottom here. So when you take the average of all these together, this is the mass number, or the specific atomic mass for that isotope. This is the relative abundance. We can figure out what element it is. So, and also remember from chemistry, honors chemistry or regular, that what makes an isotope is the different number of neutrons. Notice how the neutrons are changing, but the protons are not. But if you add these together, you get 50, 52, 53, and 54. So I know there's no equation there, but the equation is the average atomic mass is this weird-looking Greek letter for 1 mole, because remember, N is mole. It's the relative abundance of isotope N, or X, times the mass of that isotope. Now, typically, percent abundance is given in a percent. We need to change it into decimal form by dividing by 100, and we take the decimal times the mass number to get that particular isotope's average mass. All right, so let's practice this. Now, I took the liberty of kind of getting ahead and putting down the I do. So here we have a graph, and I know on 40 there's like no little blip for you, so make sure you put a little blip there. But this graph, or data table, shows, and there's 2 ways of showing atomic mass. See how it says atomic mass AMU for the specific isotope? This has M/Z. So that still means the mass number. And then we got relative abundance. Now, there's not these individual tick marks here. It just goes from 0 to 100. So on this particular data table / graph, it has the individual percents at the top of the line. So all we have to do is convert those into decimal form and multiply it by its mass number. Now, there's two ways of doing this, and I show both ways. It says identify, so we're just going to use X for right now. So 39X, we take the percent, take it into decimal form times 39, and we get this average mass. We do the same for 40 and 41, and then we can add them all up together. Or a lot of times you will see, especially in AP, they put that Greek letter there with N equals, and we're doing the same thing, but we're adding them in a line. So parentheses for the, X39. So this is X39, this is X40, and this is X41. We don't know what element it is. Sorry, can't write 3 there. We don't know what element it is, so I can't put an atomic number here. So whether you do it this way or this way, it doesn't matter. You're getting the same number. Okay? So we have this average mass, so how do we identify? Well, we got to look at a periodic table. We have argon at 3995. This is 39113. Well, 3545, that's too far away. So let's come over here, and we got 3910. The atomic masses should generally go up as you go across and down, but sometimes they don't. So here, argon actually weighs or has an average atomic mass slightly higher than potassium, which has more protons than it has. That sometimes happens. Then we go to calcium, which is 40. So now we're past it. We're above it. So it can't be calcium. It's above the average mass here, because this is 39.13. This is also above it, so it can't be argon. Chlorine is too far away, so the only one that makes sense is potassium. So we calculated the average atomic mass, and now we identify the element. X is K potassium. Okay? All right, now, again, you can watch the video for the we do. Let me put this under the camera. So this one's a little bit different. We have the isotope number. We have the mass for that isotope, but we don't have the relative abundance. It actually says calculate the percent abundance. So we're kind of going backwards here, right? So we need to highlight some stuff. So we know that the average atomic mass, not the mass number, is this, and that's of ruthenium, okay? Ruthenium only has 2 natural isotopes. We also know that these 2 isotopes, 185 Re plus 187 Re, have to equal up to 100%. There's only 2 of them. But we can't say, oh, 50-50. We have to calculate it. So how do we do that? Well, we got to kind of work backwards. So you could do this one of 2 ways. But we're going to use X and Y. All right. Remember the formula. It had this formula where it had this N here. I don't want you getting it confused with moles. So let's use X and Y. Okay. So let me get this back under the camera so it doesn't move while I'm writing. Okay. So I'm going to do, this is X and this is Y. So we have to think, well, X plus Y has to equal 100% or 1, right? So if we know that, we can substitute in and say, okay, well, if I know X has to equal, or no, not X, sorry, my bad. We can substitute this in if we say Y equals 1 minus X. It's all algebra, okay? So if I isolate Y and bring X over, I get 1 minus X. We know it has to be 100%, so we can use these. All right? So we know that the average mass is 186.21. We know that. And that has to equal X times, and I'm going to use this mass, 184.95. And we have to add that to Y times, and Y's mass is 186.96. All right? Well, we have a Y here, and we can substitute this in over here. So I'm going to rewrite it, 8621 X times 184.95 plus, I'm going to substitute this Y, 1 minus X times 186.96. So now that we have that, it's just algebra. We got to distribute. Okay, that's going to be super easy because then we can solve for X. So I'm going to change colors so you can see where I'm distributing. So 186.21 equals 184.95x plus 1 to this minus x times that. So we get 186.96 minus 186.96x. So all I did there was distribute the x. That's all I did. That's algebra 1, 2. Okay? Now, look at the problem. How do we get our x's all on one side? Well, first of all, we've got an x here and we've got an x here. So let's combine those. And if we combine those, and I'm going to change colors, if I take this and take 184.95 and add it to negative 186.96x, I'm going to get 186.21 equals negative 2.01x plus 186.96. Okay, so I just took this and added it, and because this is higher, it's going to be negative. Okay, now, just following algebra, I can isolate x by swinging this over, and by doing that, let me get a different color real quick. So, if I take this and subtract 186.96, negative 186.96 on both sides, I get 0.75, and that's negative, equals negative 2.01x. Okay? So we're getting there. You got to kind of go through some steps. Now we got to isolate x by dividing, and I'm running out of colors, so let me try purple, a lighter purple. So if I take negative 201 and divide it, negative 2.01 on both sides, I get x equals, because you take negative 0.75, divide it by negative 0.01, you're going to get x equals 0.373. So now we have what x is. Now, if we want to turn that into a percent, we just multiply by 100, and we get 37.3%, which means this up here is RE 185. Okay. Now we know they have to add up to 100, so then we could say, I'm going to do y here. So y is 1 minus x, so y equals 1 minus 0.373, which equals 0.627 which when we turn that into decimal or to percent, we get 62.7% for Re-187. Okay, and that makes sense, right? Because your highest mass, our average mass, is 186.21. That's the mass of Re, ruhenium. So the percent abundance of 186.96 Re-187 should be the highest abundance because it should be closer to the average mass. 185, the percent abundance should be lower because it's farther away from the average mass. Okay. All right, so you're going to use the I do practice and the we do practice to solve for number 1 through, I believe we have several examples, 1 through 4. Okay, so number 1, let's go over the questions. You got the mass spectrum of a sample of a pure element below. Calculate the average mass of the element and identify. So we've got, let me get a different pin here that's darker. You've got X24 that has a percent abundance of 0.7899. Then you've got X25 with a percent abundance, that's 10. When you divide it by 100, you're going to get 0.10. And then you got, so you got 3 isotopes. And then you got X26, and it's got a percent abundance of 11.01, so 0.1101. Okay? So this is just like number 1. So either do it this way or do it this way and identify the element. Number 2, determine the most likely element for the mass spectrum given below. Justify your choice. So we got the percent abundance here. We got 90, 92. This is 91 right here. So 91. And 94 and 96. So we got 1, 2, 3, 4, 5. So we got 5 isotopes. So you can tell that. You're going to have to, you're going to have to take a ruler and kind of figure out their percent abundance. So this is 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. So I would take a ruler and go across with each one of these points to figure out the percent abundance and just do what I did in number 1. X90 looks like it's closest, let me see, maybe just slightly above 50, maybe 51, okay? And then you got X91, it's definitely above 10, maybe between 10 and 20, and so on. Oh, and 96 is really, really small. Okay, 1, 2, 3, 4, 5. Don't forget, you got 5. So it's really small, so you're going to have to estimate and then line it up to the mass of tungsten, niobium, zirconium, plutonium. Now you could say, well, it should be closest to 90 because that's got the highest percent abundance. Well, let's see where 90 is. 90, 90, 90. We've got 88, 91, 92, 95. So you definitely got niobium in there. You got zirconium in there. Tungsten is W. That's 183. I don't know. Plutonium is way down here. Plutonium it doesn't even have a mass. So you can kind of eliminate 2 of them right off the bat. All right, so number 3. You're given Z. That's another way. Sorry, I'm off camera. That's another way instead of using X and Y. So you got Z isotope 85, 87, 85. Has a natural abundance of this and a mass of this. Or Z85 has a percent abundance of this and a mass. Z87, there's its mass abundance and its mass. So with that, calculate the average mass and determine the identity of a Z. So it looks like it's 2 isotopes, and you're given the percent and the AMU average for that isotope. So this is just like number 1, just without a graph. And then number 4, 84 has a little blip right there. So this has got 4 isotopes. 1, 2, 3, 4 lines. So I would put them in order. It says label and identify the first, second, third, and fourth. You can use, X84, 86. You need to fill in the information. You can't do protons or neutrons until you figure out what element it is. Okay? So you need to figure out what element it is by doing the mass spec for number 1 for the 4 isotopes. Then you can put the symbol, just like I did for chromium here. You can either write it out like this, or you can put the symbol with the mass number and then the number of protons, which is the atomic number. However you want to put it in the table. Once you know the atomic number or number of protons, protons minus the mass number gives you neutrons. So mass number minus protons gives you the neutrons. Okay, and this is the average that you find from this. Not 84. It's 84 times this percent to get the average mass. The relative abundance would be this number. Oh, sorry, I'm off camera. The relative abundance would be this number up here once you divide it by 100. Okay? So, just to help you out, I'm going to let me see if I can sort of help you out on one of them. And you can do, you can do like x84, however you want to do it, or you can just put 1, 2, 3, 4. The mass number is, you're not multiplying those and putting it there. You can put the mass number of 84 there, okay? The relative abundance is what is up here, so 0.56%, or you divide it by 100 and you get 0.0056. Either one would work. But you got to figure this out by calculating what element it is. So until you know what element it is, you can't put isotope, protons, and neutrons. Okay? All right, and that is mass spectra of elements, topic 1.2 for AP Chemistry, and I will see you in class.